Welcome back to System Software. Today we're going to start our section on the system software, and we're going to start with files and looking at the basics of files. Before we begin, let me go over the homework from last time. So the first question was, do make files use tab characters or spaces? They use tabs. Be sure to, when you're doing indentation, make sure you're using a tab character itself, not a space character. In this makefile rule, what is the target? The target is hello, the name that comes before the colon. And the target is the file that will be generated by the rule, or that's supposed to be generated by the rule. The developer tells the make system what's going to be generated. The prerequisite is this part here after the colon, and this tells make that any of these files that are listed as prerequisites, these must be created before we can generate the target. And so this is useful for automatically recompiling only part of the source files that need to be compiled. So if you edit the hello file or change its timestamp in any way, and its timestamp is newer than the target file, then make will rerun this rule. Otherwise, if hello is more recent than the prerequisite, then this rule will not be rerun because we assume that the files used to generate hello have not changed since hello was generated. Now remember, this is all a convention. It's up to you, the makefile writer, to make sure that the instructions that inform up the rule, the recipe, actually do generate the target and depend on the prerequisites. And the recipe is the sequence of instructions, sequence of commands that appear here, indented with a tab space after the target and prerequisites. And this is the code this is the commands that will run whenever make determines that the target is out of date, that it needs to be regenerated from the prerequisites. There was a question during the class on phony targets. Phony targets just tell make that this target is not actually a file. So every time someone asks to build this target, always run the recipe, even if the file will just never meant to exist on the file system. So if you happen to have a file that's also named the target, it won't look to see if it needs to be regenerated. Instead, it'll just run the phony target. So a common phony target that you'll see is clean, and by convention will remove generated files like hello. Last question in the above rule: what happens if you run make twice in a row, assuming hello.c builds successfully? The first time this rule runs, hello doesn't exist, so make will look at the prerequisites, make sure that they exist, and then run the recipe in order to generate hello. So hello will be generated already. When we run make again, because hello has been generated already, it exists, and hello.c has an older timestamp, it has not been updated since we first generated hello, then it won't run again. It'll tell you that targets are up to date. Okay, so that's homework 4. Let's get into our main lecture on the file system. This is probably, if you think of files, this may be the kind of image you think of when you think of files. This is an application that's on many graphical operating systems that helps you navigate the files on your disk in your file system. But strictly speaking, this is just an application that uses the file system in order to give you information about it, in order to help you to explore the file system. But it isn't files itself, per se. Instead, to understand what files are really just an abstraction. They're not specific to storage media. They're not specific to storing information on a disk. They're actually an abstraction that the operating system, the kernel, provides to you for any interaction with hardware or any interaction with some software where you want to read and write sequences of binary data. This is really, at its core, all files are. There's no naming, like file names. There's no specific hardware. There's no specific application, like storage versus networks. And there's no file formats that are intrinsic to the file abstraction, which we'll talk about more later when we get into file extensions. So why is it an abstraction? Because it just captures what's common about storage hardware and other I/O contexts, but it doesn't include any of the specifics, like I have a directory, or I have a hard disk, or I have a flash disk. So there's a lot of different data storage technologies like magnetic disks, spinning disks, optical, flash, RAM, and there's lots of things that are different about them. The actual physical properties that they exploit to store data, the bus or the hardware protocols that are used to communicate with them. But what's common about them is that they all can be thought of as ways to read and write sequences of bytes. That may not be the only way to use them, but we can use all of these different I/O devices as mechanisms for reading and writing sequences of bytes. And what files do at the kernel level and the operating system level is they abstract away the specifics of the physical hardware while leaving you with that same common mechanism. They let you read and write sequences of bits to them. And what file systems do for on-disk storage is they group together these sequences of bytes on the physical medium, and they provide you this large addressable sequence of bytes for one particular file at a time. So the abstraction is used. So I like to define abstractions by how they're used. I think the good way to define an abstraction is to look at how it needs to be used and define its interface. And we get two common simple things, which is reading and writing. Let's take a look at the contents of a file to kind of illustrate what makes files, what is stored with files and what's not stored with files. So here's a utility hex dump, which will print out in hex the sequence of bytes that are stored by the file system in the operating system in the file that's being referenced with hello.c. So you can see here's all our printable ASCII, and then this part on the right here is a feature of hex dump. This -c will give you the ASCII character interpretation of these bytes on the right here, so we can see that we have the ASCII characters that we expect in our hello.c file. This is just a simple hello world file. And it gives us the ASCII bytes, and for any non-printable ASCII characters, it will give us dots. So that's why it looks like this linear compressed sequence of ASCII characters. But strictly speaking, the contents of the file is just a sequence of bytes. There's nothing intrinsic in the file that makes this a text file versus any other kind of file, or at least there's nothing in the file system that dictates this. So then what about extensions to a file? So I've called this a .c file. And indeed, if we look at it, it looks very much like a C source file. But I could just rename this. I could copy this to another file called, say, MP3. MP3 files are audio files. And the contents of the MP3 file, so here I'm going to dump the contents, are identical. Nothing about the file changed when I changed its extension. And that's because extensions are really just a convention used by applications. There's nothing, at least in Unix-style operating systems, that gives any meaning to the extension. The file itself, the file which is controlled by the kernel, is oblivious to that extension. And you may have, and this is related to a philosophical principle called the map is not the territory, or the map-territory relation. So if I redraw borders on a map, that's not going to make the physical borders change. If I redraw the path of a river on a map, it's not going to actually change the physical world. Instead, the map is just a representation of the physical world. And it's the same thing here, where if I rename this file, that doesn't actually change any content of the file. You also may encounter this with pointers in C. So if you try to write the actual pointer data itself, you're not going to change the data that's being pointed at by it. Instead, you're just going to change the address that you're pointing to. Now, there is a tool called File, which does look at the contents of the file and try to infer what type of file it is. So if I give it file hello.c, well, it tells me, hey, I think this is a C source file. And I see only ASCII text, so I think it's an ASCII file. I only see binary data that is within the range of ASCII encodings. And it uses other tricks to see, I think this is a C source file. So if I give it that MP3 file, even though, or that purported MP3 file, even though I've given it the MP3 extension, it's still going to, by looking at the contents of the file, it's going to say, I think this is a C source file. If I give it a genuine, correctly formatted MP3 file, it's actually going to figure out that, hey, this is an MP3 file. So the name of the file does not have any bearing on the contents of the file. And if you look at the file command, it tells you its algorithms for determining, trying to guess what these files are. So it tries to look at it looks at what the actual file system says. It uses a series of magic bytes, which I'll show in a second. And it also tries to look at programming languages, tries to figure out what programming languages it might have. And you can look at all the details here. It's a pretty cool utility. One thing it has is this database of so-called magic bytes. So these are just some types of files that you might encounter. So it uses these so-called magic bytes. So let's take a look at, let's dump the contents of this actual MP3 audio file. And I'm just piping it to head so I don't see all of the contents. And you can see here at the even though this is a binary file, it contains binary data. It's not supposed to be readable by an editor. It's supposed to be readable by an audio player, which reads the bytes in. It actually does have some printable ASCII characters. And at the very beginning, there are these 3 bytes that correspond to the ASCII characters I, D, and the symbol 3. And it turns out that by convention, many binary file formats have a predefined set of magic bytes, or 3 bytes, at the beginning of the file that indicate what kind of file it's supposed to be. And so this is a case where, by convention, certain file formats will use the contents of the file to define, to help indicate to applications what kind of file it is. And this is in the contents of the files. And so this file tool, this command called file, has a database. This is the source code here on the left. This is the source code of the file command. And in here, it has a big database of all of these so-called magic bytes. And here you can see, if it sees the magic bytes ID and 3, that it corresponds to an audio file. And there's a whole sequence, a whole large database of these magic bytes that go into the actual file contents. And so you can see here that by the same token, if I rename or copy this actual audio file to have a .c file extension, the file command won't be fooled, because it doesn't just look at the extension, it looks at the contents of the file and it sees that it has these magic bytes. Now, strictly speaking, these magic bytes also may not necessarily tell you what the file is, because the person who created that file could lie. They could take a video file or an executable, and they could put these magic bytes at the beginning to try to fool tools like file into thinking that, yes, it is an audio file, but in reality it actually contains bytes of a different type. Strictly speaking, bytes are just bytes. They don't have any meaning until they're interpreted by some computer program, some application. So even these bytes of the audio file, these are actually the metadata about the audio file, but if we were to look deeper inside the audio file, we'd find raw bytes that, when processed by an audio app, an MP3 decoder, and processed by an audio application, are turned into sound. But strictly speaking, the bytes themselves don't have any meaning outside of an interpretation by an application. And I also have an example here of an executable file. So here's my executable file, and here's what the beginning of that executable file looked like. It has this .elf magic bytes. So this refers to the executable and linkable format. This is the executable and linking format that is used to store executable code in Unix-like operating systems. So this distinction between the extension of the file, what it purports to be in its name, and the actual contents, has consequences for security. So you can read through a whole section in MITRE on these kinds of so-called masquerading attacks, where attackers lie about the kind of file it is, sometimes through the extension. So here's one of the earliest and large-scale computer worms that spread itself through, I think it was Outlook. It was through Windows, Microsoft Outlook email application. And the way it worked is the attacker sent a VBS file, which is a Visual Basic Script. It's a runnable, executable scripting language. And they just called it .txt, which is the extension for text files, .txt.vbs. Because by default, in Windows at the time, and I believe still now, the extension is hidden, what users saw is love letter for you .txt. Now, you may be thinking, well, there should be an extension, but it's easy to kind of miss this kind of thing. And so users may have clicked on this thinking it was a text file, but in fact they were executing code from this attacker, and that code would replicate itself by sending this letter out to everyone, I believe, in the target's set of contacts in their address book. So here's a case where the extension does not match up well. What the perceived extension is does not match up with what it actually is. And there are actually attack scripts that will also exploit this to kind of obscure what kind of files are being shipped. So here we have an attack script that's renaming a file from txt to exe, so then it will be picked up as an executable if run by the user or run by some other part of the system. So you can read more about this on the links that I have here in the notes. But this kind of masquerading attacks are, they're pernicious, and they've been used quite a bit. And they also reflect the fact that the name of the file has little to do explicitly at the system level with what the actual contents of the file are. If you've heard of the more recent XZ-utils backdoor, where a compression library was used to insert a backdoor into SSH, that secure shell command that we all use to connect to Eustace. Lots of other machines use this. They masqueraded binary code as a test file. They took a test case and they pushed it to the code repository in its test folder, and it made it look like a test case, but actually it contained attack code that would attack scripts and also binaries that were used to add a backdoor to this library, which would then be inserted into SSH, an SSH server. Okay, so files don't reflect in the system, they don't reflect the contents of the file. How do they get their name? And they get their name through directories. And all directories are maps from the names of files to the file itself, or to what the system numbers that file to be. So think pointers in C. The pointer to the integer is not the actual integer, or names in a phone book. When you look up in a phone book, you have a directory, which is why directories are probably called directories, and they list names and they list a phone number. And that phone number is not intrinsically linked to that name. Somebody could lie, somebody could move, and that name no longer maps to that phone number. And by the way, you can also have multiple names to the same phone number if they say live in the same house. So under the hood, the system doesn't use names for files. It gives them unique IDs. These are called inode numbers. And I hope you'll read the Unix paper that's assigned for reading for today. It's a really good read. It's not a long read. And it'll give you insight into the basis of the system design that really is in all systems that we have today. The big major systems, Mac, Windows, Unix and Linux, other Unix distributions like BSD. They all can see their lineage in a lot of the design decisions that were described here in this paper. Not all the design decisions were totally new. There were some novel ones, some reused ones, some reworked ones. But this will give you, in a simple, readable paper, a description of the design decisions. And so one way that the file system works is that the system, whenever you create a file, the system creates a unique ID for this file. And this, depending on the file system implementation, will give you the entry point to find that whole sequence of bytes that comprise the contents of the file. And these are called inode numbers in the Unix world. And you might be wondering, why even bother separating the name from the file? There's a number of reasons why you might want to do this. So one is that renaming is very easy. So instead of, if you want to move into a house, you don't have to necessarily change your number. You can just keep the same number and change who lives there. Or if you change your name, you can just change your name. You don't have to change the phone number to the house or the phone number to your cell phone. And as we talked about when we did the lecture live, you can also give many names to the same file. So you don't have to have a single name for them. You can actually have multiple references to the same file from different parts of your file system. And what about directories? So what are directories then? How are they stored? Well, directories are also just files. So from that paper that I've given you for reading for tonight, directories behave exactly like an ordinary file, except that it cannot be written by unprivileged programs so that the system controls the contents of them. So the way this works is that directories, from the file system perspective, they're just sequences of bytes. They're just a file that has a name that maps to an inode number. But instead of allowing users to directly touch these files, the system itself will control this directory listing, and then through the system, like instructions like make directory or move, you can modify the directory file, but you can't read and write to it directly, say, from an editor. But otherwise, they're just sequences of bytes that can be read or written to, just like any other file. So here's an example of what a directory file may contain. Now, how this is actually stored in bytes is system and file system specific, but at the end of the day, what you get is a table that maps names, string names, to these inode numbers, what the system actually uses to call these files. And with the -i flag to the ls list command, we can actually see this mapping. So we have the name of the file and the inode number. So they're a little different here. This is from last semester. The inode numbers are different, but the file names are the same. So another benefit to having this is if I say copy this to someone else's machine or copy this to the server, I'll have the same names of my files, the same naming structure of my file system, but it's kind of irrelevant how
the file system stores these. They don't necessarily have to have the same name. They don't even have to be on the same type of file system. Okay, so in this scheme, if I want to move a file or rename a file, what's one way to implement this? So one way is you just copy the whole file and delete the old one. But because the name of the file is detached from the actual inode number or the contents of the file, moving a file, so let's say I move this hello program to a newly named hello program, then what's going to happen to my directory listing? Well, you can see here that previously my hello program had this inode number, 490.345.02, and in my renamed program, it has the exact same inode number. So I didn't actually have to do anything to the file contents. I didn't even have to do anything to the inode number or the file system. All I had to do was change this directory file. So the directory file is a different file in the file system. And I didn't have to touch anything else except this directory file. All I had to do was change this name here and leave everything else the same. So it makes moves really fast. It also means that moves and renames are identical. So that's why there is no rename. I think there actually is a rename command, but there's no core utility for renaming. You just use move to do that. Move will do renaming. So move is just editing these directory listings. And so also, just by the way, this directory file is a file, so it itself also has a directory listing in some other directory. Okay, so to motivate this, the question is, can directories contain other directories? And the answer is yes, because directories are just files. And if directories are just mappings from names of files to their actual file inode number, then directories also have inode numbers, and they can be contained in other directories. So to show this, I've made a new directory called subdir, and notice that subdir has its own inode number. And if I enter the subdir directory with cd change directory, then I can start creating files in here. So file in subdir. So the subdir directory file has its own listing of files. I've created a new file here called with this inode number, and it's called a file in subdir. And if I go back to my parent directory, remember cd ... goes to the parent directory, you can see that subdir has its own listing in my file basics directory. And if I list the contents of the subdir directory, I can see its directory listing, and I can see the file in that directory. So this is how this file hierarchy is formed. It's just formed from the fact that file names are separate from files. Instead, there's a directory listing that maps names to file numbers. And that directory listing itself is a file. And I can reference that file in a directory listing. And when I reference a file that is a directory file in a reference listing, that becomes a subdirectory. And this whole path business that we learned about when talking about the command line, this comes out of the fact that I can have directories within directories, and the path is just a naming scheme for capturing a sequence of nested directories. And so this is what happens when directories contain other directories. We get a hierarchical file system where directories can contain other directories arbitrarily, indefinitely, and you can represent this with a tree structure of directories. So this is the file system hierarchy. And so just a quick review of this from the command line class. In Unix-like file systems, the top of the hierarchy is always the root directory. And the root directory is always called /. Now, we also separate files, separate directory names with a / as well. So if we say have a file hierarchy where the root has a home directory and the home directory has a pol directory and the pol directory contains hello.c, then by convention, if I want to refer to the full path to reach this hello directory, I say / for to start from the home directory. Start from the root directory. I put a subdirectory, the name of that subdirectory under the root directory. I use the / to separate and indicate that I'm now talking about a subdirectory of home, and so on. So I put the pol subdirectory, put a file separator here, and then I put the name of the file. And so the absolute file name, the file absolute path, tells you, starting from the root directory, how to follow the subdirectories, the hierarchy of subdirectories, in order to reach the directory entry for the file that I'm trying to refer to. So that's where this path comes from. That's where this directory file hierarchy comes from. That's where this path comes from. Just a set of subdirectories to follow in order to enter and find the directory entry for this hello.c file. So I could have other children of the root directory, but this path tells me how to uniquely follow a path through the tree to find hello.c file. This also tells me how to refer to relative paths. So for instance, if I'm currently in the home folder, if this is my working directory, and this is my working directory, let me put the path separator here, and I refer to the relative path pol / hello.c, then we can always find the absolute path by taking the relative path and concatenating it or joining it using the correct path separator, joining it with the working directory. That's the origin of relative paths and absolute paths. Okay, so additionally, we've got, by convention and by design of the Unix-like file systems, two special directory entries. These are the dot and dot directories. So let's take a look first here at our directory listing for the file basics folder. And then let's look at the directory listing for subdir. Now, if I want to show you now by default, ls does not show so-called hidden files. Hidden files are those in a Unix-like file system that start with a dot. And we can see here with the -a flag to ls, we can show the dot files as well. And you'll notice that there are two files that start with a dot. One is just dot by itself, and one is two dots. And notice that the file node number of the dot folder is the same as the file inode number as the subdir was in the file basics folder. And that's why the dot folder actually refers to itself. That's why if we're inside of subdir and I want to see the inode number of the dot folder, then it is the same inode number as it was in its parent folder. The parent folder of a subdir is file basics. The file basics directory entry contains the subdir file. And inside of the subdir file, there's a directory entry for itself that refers to itself. And there's reasons you might want to do this. For instance, by default, ls will list the files in the current directory. But if I want to say list the files in bin and the current directory, then I have no way in the current directory to refer to the current directory itself. So the dot entry, which will always appear in all directories, is a way for me to refer to the current directory itself using a relative path. I could use an absolute path to do that, but having a relative path is convenient to be able to do that. So I have the absolute path to bin and the relative path to the current folder, and now I can list them all. and I'll get everything in both folders. So, okay, I've also got the ... folder. So let's show the ... folder. So here, the ... folder is the parent directory. To see the parent directory's inode number, so the parent directory here is file basics. So to see the parent directory's inode number, we can list the inode number of file basics in its parent. So its parent is Scratch. And in the Scratch folder, we have an entry for file basics. And file basics has this inode number. And you can see that when I refer in the subdir folder, when I have the ... folder, it's referring to the file basics folder, which is the parent of subdir. All right, let me show this in the hierarchy to make this more visually clear. So under each of these directories, even though I haven't shown them on this hierarchy here, there are two additional directory entries. One is the ... directory entry. And I'm going to use this dashed line to refer to the fact that these are referring to the same thing. These are referring to the exact same file on the file system, and that's the file that's represented by the inode number that you can find mapped from the Paul name. So there's some directory file that lists hello.c and the ... folder, and that file is referenced by both the Paul directory entry in the home folder and also by the ... directory in the Paul folder. There's also a ... folder, which is linked. It refers to the same file as the parent of Paul, which is the home folder. So if I have a path, say from root to home to Paul to ... let's say if we have a file in here, if we also have a file in here called hello.c in the home folder, and I refer to home Paul ... hello.c, which hello.c am I referring to? Am I referring to this one, or am I referring to this one? Well, let's follow the file paths. I'm starting at root, and I go to the home folder. I'm in the home folder. And then I go to the Paul folder. Here's the Paul folder. And then I go to the ... folder. The ... folder is synonymous with home. So now I'm currently in the home folder, and when I go to hello.c, I'm referring to this hello.c. So the ... is a way in a relative path, or actually even in an absolute path, is a way to refer to the parent directory of whatever the previous directory was. Okay, so that's root, and ... I've gone through an example file system hierarchy here. I've shown you paths, so this is an absolute path. I've shown you relative paths. We've talked about the working directory. We've talked about parent directories. And so just a quick review of the command line for, so this is tonight's homework. So just, a quick review of the command line here. So to navigate our file system, we can use the cd command to cd for change directory and give the name of a subdirectory to change into. Remember to use tab. So I'm only typing su here, or s, and hitting tab. That's why it's so fast. And actually, even if I don't type anything and just hit tab, because there's only a single subdirectory, it will autocomplete for me, autofill in the name of it. ls to list the directory, list the files in the directory. You don't have to remember -i and -a, and I even use -d here, which is another option too. Only list instead of listing the directory contents, list the directory itself. You can see more about ls with man ls, remember, is the man is the man page. cd ... will change directory to the parent. Remember that this bash shell is configured to prompt you with the current path of the directory that you're in. Let's see what else we had. mkdir to make the directory. It's already created, so it's going to yell at me. rmdir to remove a directory. So notice here that the rmdir command by design will not remove a directory if its directory is not empty, because it's, remember, directory is just a directory. It's a mapping from names to file numbers. So if I remove the directory, if I delete that file, well, now we have all these orphaned files that the file system thinks exist, but the user has no way to actually reference them through a path. So what we need to do is remove everything in that directory first. So I'm just going to remove them one by one. And then once that directory is empty, then we can remove the directory. There are ways with wildcards, for instance, to remove everything from a directory. And there are also even ways to recursively go through the file system and remove everything. So there's a feature of the remove command, which will recursively remove. And remember, this is a tree. So what's the algorithm for removing? What's an algorithm for removing everything, including all subdirectories? Well, it's a classic tree walking algorithm. You have a post-order tree traversal. You go to the left, or you go to all the children, recursively delete everything from there, which will go to all the children until we reach a leaf, delete the leaf, and then once all leaves are deleted, you can delete the parent, and so on. Okay, remember touch creates an empty file. Move does rename and move. Emacs, it takes two arguments, move the old file and the new file. Emacs to edit stuff, Emacs to edit stuff. Also, one thing I didn't point out is that move will also move between file hierarchies. So right now, hello.txt is in my file basics folder. Move will also put them into a different subdirectory, a different directory. So here I'm moving it into subdir 2. And what does that algorithm look like? Well, I just look inside of the directory in my current folder, or the folder that I'm moving from, and I remove that entry from my current folder, and I add it to the directory, add a directory entry for it in my destination folder. So here I didn't even put the name of it, I just put the directory. You can also put the name, and it'll change the name of it. Okay, so those are command line review. So just to review, remember the file abstraction is just an abstraction. It's not only for storage, it's also used for network sockets, pipes, buffers, in-memory buffers. Somebody asked about in class. You can even, there's even a special file for memory. So there's a /dev/mem special file that will actually touch your physical RAM. You need root permissions to do this. Don't do that. It could cause issues to the stability of your system. But even arbitrary hardware devices like memory itself has a file that you can use, file IO, to communicate with it. Peripherals, temperature sensors, little microcontrollers, all you can use. Networking also uses open and close, open and read and write. Has a different open and close function, but you can use read and write to communicate over network sockets. So basically all I/O on your system can use files technically, even though they don't always do that. So sockets have a different software stack called the TCP stack for opening, reading, and writing to sockets, but it uses a similar system call for reading and writing. And so these are really topics for an operating system class: how this is implemented, how permissions and security work, this kernel design, different types of files, networking. So thing to remember is that file is just an abstraction. It's not the file browser. It's not your hard disk. And this abstraction is created by the designers of the kernel, the people who wrote the operating system. They are the ones who provide this idealized version of input and output to access your hardware. File hierarchies emerge from the fact that directories are also files, and they just store a mapping between names and the inode number. And we learned about paths, this path convention, which you also probably have seen in URLs, which draw from this path convention. Okay, and that's it for this class, and we'll see you next time.